of a tutorial looking at tension and Newton's laws of motion. I'm going to work through. So here's a scenario. Person pulls equally hard on two massless strings that are attached to a block as shown at right. The strings remain taut and symmetrical, forming the same angle at the horizontal at all times. So that angle is that angle. Okay? Draw an arrow to indicate the direction of the acceleration of the block for each of the four motions listed below. So the block is speeding up while moving downward. So the velocity is down and it's speeding up. So the acceleration is pointing in the same direction as the velocity. So there's the acceleration. Block is slowing down while moving down. So velocity points down, but it's slowing down. So acceleration points up. Block speeds up while moving up. So velocity is pointing up and it's getting faster and faster, so the acceleration points up. Block slows down while moving upward. So velocity is up, but it is going slower and slower over time, so the acceleration points down. All right, draw an arrow to indicate the direction of the net force for each of the four motions. Well, Newton's second law tells us what to do. I add up all of the forces on an object, and that equals the mass times the acceleration of the object. So whatever the direction of the acceleration vector, that's the same as the direction of the net force. So acceleration is down, that means the net force is down. Acceleration is up, that means the net force is up. Net force is up, net force is down. Okay. Explain the reasoning you used to determine the direction of the net force for each of the four motions. We use Newton's second law. I add up all of the forces acting on an object, and our shorthand for that sum of all forces is the net force. That equals mass times acceleration. Since mass is positive, we know that those two vectors, net force and acceleration, have to be parallel to each other. Draw and label a free body diagram for the block for each of the four motions. Indicate relative magnitudes of the forces by the relative length of the force vectors, and draw all diagrams on the same scale. All right, so I need to have a net force that points down. So there's my weight of the block, and then I have a tension to the right and a tension to the left, and these are going to add up to give me a net force of tension that's straight up and smaller than the weight. If I can draw a parallelogram correctly. So that's basically the same free body diagram for the block in this case as in this case. So let me just go ahead and draw that again. The weight doesn't change. It's still mg down, and our shorter forces of tension to the right and to the left. All right, so these two middle cases, it's actually accelerating upwards. So the net force points upwards, and I have to maintain the same angle. So the magnitude of the right tension always has to equal the magnitude of the left tension. Weight doesn't change, so it's the same, and now I'm just going to make bigger arrows for the force of tension. Now I add those two tension forces together. The horizontal component cancels out. I'll get a vertical component, And the net force of tension is going to be bigger than the weight. So I have the net force up. And then in this case, the drawing is going to be the same for the free body diagram. Tension to the right, tension to the left. Okay. Let's see what's on the next page. The next page, let's read. Consider the following statement made by a student about each of the four motions in problem 1. The magnitude of the force exerted by the block on an individual string is the same as the magnitude of the force exerted by that string on the block. Completely agree. That's Newton's third law. That's awesome. They are a third law force pair. Yes. Awesome. Doing great. So I don't understand why the block doesn't move at constant speed if that is true. That's where they went off the rails. First two sentences, awesome, good physics. That sentence is bad juju. So here is what you really need to read carefully and think through carefully. Exerted by the block on a string. So by the block on a string is the same as the magnitude of the force exerted by that string on the block, right? Okay. It is irrelevant to the motion of the block what force it exerts on the string. The force that the string exerts on the block is always going to be equal and opposite to the force that the block exerts on the string, but only one force in that pair is a force on the block. So when we add up all of the forces on the block, it cannot include a force that's on the string. So Newton's third law is not a mechanism to get us to a sum of forces is 0 on an object. Forces will always come in pairs. You're not going to be able to violate Newton's third law of motion. That does not mean that objects can't accelerate. Okay? At this moment, I am sitting in a chair. I am exerting a force down on the chair. That force is equal and opposite to the force of the chair up on me. I can sit up out of my chair just fine. I'm not doomed to just sit and remain at rest in my chair. Okay. The student has correctly identified a Newton's third law action-reaction force pair. Explain why this does not mean that the block must move at constant speed, right? We need to examine forces on the block to determine motion of block. Forces on the string is a different matter. Okay, that would tell us how the string is going to move. All right, we've got a fun little scenario here. I have 5 identical blocks, 1, 2, 3, 4, 5, each of mass little m, and are pulled across a table as shown. So pulling on string P. Use the approximations that the table is frictionless and that the strings are massless. Okay? Describe the motion of each of the systems A, B, and C. So I've got a system A that is just block A, system B are those 2 blocks, and system C are the last 2 blocks stacked together. So how are they going to move? I pull on string P, and these are all going to move together. So they will all accelerate together. And I'm assuming there's a sufficient force of static friction to keep these two blocks together and keep those two blocks together. Otherwise, if there's like no friction at that interface between the two blocks, then this bottom block is just going to slide out, and this top block will be hanging in midair, precisely as bricks do not, and then fall. Okay, so we're going to assume that that's not the case. There's no friction between the block and the table, but there is sufficient friction to keep these blocks accelerating together. Otherwise, we have a much harder problem to analyze, because the mass is going to change and blocks are going to hit the string and it's going to be a mess. So assuming static friction between two blocks and B and C is large enough. All right, draw vectors below to represent the acceleration of each system. They're all going to accelerate together. Let me say a little bit more about that. If that were not the case, if the acceleration of each system were not the same, then I would have a situation where like system A is pulling ahead, these guys are behind. I'm stretching out that string. That's not what strings do. Or even more interesting would be, let's say system B and C have a greater acceleration than system A. Well, then they're going to pull ahead and run into it. And that doesn't make any sense. What is ultimately making system B and system C move? They are being pulled by this tension. String Q is pulling B and C together, and string R is pulling C. So they're all going to accelerate together. They can't have different accelerations with some faster than others. All right, draw and label separate free body diagrams for each system's A, B, and C. All right, so A has the smaller weight because it's only one block. So let me try to draw that smaller. There's an mg. And there is a normal force on block A. Let me see. The net force is going to be enough to accelerate this block, the left. So I'm going to have a pretty big force, and then an almost as big, but not quite as big, tension in Q. So system A, that one single block, has a net force to the left, and that provides its acceleration. All right, so let's look at system B. I need to make the weight twice as big. So that looks right-ish. And it's not going to fall through the table. It's not going to spontaneously jump up off the table. So there is a normal force, just big enough to cancel out that weight. There is a force, the vector is just as big as this vector, but it points in the opposite direction, because our string is massless. So the tension is the same magnitude at both ends. The tension is uniform throughout that string. And there needs to be a net force to the left. So this guy is a smaller tension from string R to the right. And the difference between these two tensions should be, if I drew this out correctly, twice as big as the difference between those two tensions, because this block has twice the mass. its net force is twice as big as for system A. All right, system C, 2 blocks. The weight is the same vector, so the blocks are identical. And now I have a normal force C that cancels out the weight, and I'll have a vector for tension in string R pulling to the left, and this arrow should be just as big as that arrow, but pointing the opposite direction. Okay, rank the magnitudes of the net forces on systems A, B, and C. Explain. All right, the accelerations are the same because they have to move the same. I'm not going to have one of these systems catching up or falling behind its neighbors. So the acceleration is the same. Newton's second law of motion tells us I add up all of the forces in a system. That gives me the net force, and that is the mass times the acceleration. Okay. Acceleration is the same, but the masses are different. System A has half of the mass as systems B and C. Therefore, the net forces are not the same. The net force has to be bigger for systems B and C than for A. But B and C, they're identical. So the ranking, the magnitudes of the net forces, C is going to have a net force that is just as big as for for B, and those are both bigger than the net force on system A. Write expressions for the tensions in strings P and R in terms of TQ. Tension T sub Q, the tension in string Q. Show all your work. Well, just read it off from our free body diagrams. Which of these tension arrows is tallest of allest? Has to be this guy. So TP minus TQ is going to be mass of one block times acceleration. We also are going to know TQ minus TR is 2 MA. And TR is going to be 2 MA. All right, so we know TR. That tells me that TQ, move that to the other side, is going to be 4 MA. Move that to the other side, it's going to be TP, be 5 MA. All right, so what do we know? So in terms of TQ, TP is 5/4 TQ. That works out. Substitute in 4 MA, 4 cancels out, and I'll get 5 MA. And then TR, 2 MA is TQ over 2. There we go. Expressions for the tension in strings P and R in terms of T sub Q.